Hello, everybody. How are you guys all doing? Hopefully you're doing well. So today what our game plan is we are going to talk about the SN2 reaction. So remember in class on Monday or in lecture on Monday, we discussed just very briefly the introduction into chapter 9, which was the nucleophilic substitution reactions, SN1 and SN2, and the beta elimination reactions, E1 and E2. Okay, so what our game plan is here for the next couple of lectures. So today we're going to talk about the SN2 reactions, and this will take us a lot of the class period because we need to go ahead and address all the various aspects that kind of govern whether or not our substitution is going to follow an SN1 or an SN2 pathway. And then on Friday, we'll talk about the SN1 reaction, and then we'll try to come up with some criteria, given the various components of a reaction, including the starting material, the reagents, and the conditions, how we can decide between the SN1 and the SN2 reaction. And then from there, we'll introduce the elimination reactions and see how really all four of those reactions, SN1, SN2, E1, and E2, are in competition with one another, and we'll come up with some criteria to go ahead and figure out which mechanism would operate to the greatest extent. Okay, so the SN2 reaction. So we already talked about what the S and the N stand for, but I'm going to go ahead and reiterate that. So the N stands for nucleophilic, and the S stands for substitution. Okay, so we're thinking about nucleophilic substitution reactions. And the 2 is telling us that this is a bimolecular reaction, okay? And that's in terms of the rate expression. Okay, so we're gonna look at some rate expressions today and on Friday in class to a very brief extent, just to think about how the concentrations of the various starting materials and reagents influence the overall rate of the reaction. And so the SN2 reaction is bimolecular, and that's going to mean that there's 2 molecules whose concentration is going to govern or impact the rate of the reaction. Okay, so the first thing that I want to do is actually not necessarily look at an example, because there's a wide variety of starting materials that could operate under the SN2 mechanism. We looked at an example in class on Monday, which was acetylide substitution. So I want to just jump in with the mechanism here. And then we'll think about how the mechanism can influence, the various aspects of the reactions and their preferences. Like, for example, what starting materials in terms of the electrophile would be preferred and what nucleophiles would be preferred. Okay, so let's go ahead and start off with the mechanism of the SN2 reaction. Okay, so here we're going to look at a generic nucleophile, and we'll look at specific examples as we go throughout class today. Okay, and then we have our electrophile. All right, and right now I'm not going to qualify whether these R groups as general substituents are, hydrogens or carbons. We'll talk about how the substitution of the carbon that bears X, the leaving group, influences this reaction. Okay, but I want to use this as an example so I can show the transition stated, and that will have a consequence on the overall stereochemistry of the reaction. Okay, so in the SN2 reaction, this is a concerted single step mechanism. So all the bond making and breaking happens at the same time. So this mechanism is acetylide substitution. So imagine the nucleophile was acetylide and the electrophile was our alkyl halide. This is the same mechanism we drew there. Okay, so we have the nucleophile attacking the carbon, and then we kick out the leaving group. Okay, so we're actually going to draw the transition state of this single concerted step mechanism. Okay, so let's just make a note over here that this was a concerted single step mechanism. Okay, so remember when we say concerted, we mean the bonds that are breaking and the bonds that are forming, or that process of bond breaking and making is happening at the same time. Okay, so at the transition state, what would that look like? Okay, so we are making a bond between the nucleophile and the carbon, and we're breaking a bond between the carbon and the leaving group, the X group. Okay, so there is a 180-degree relationship between the nucleophile and the leaving group, X. Okay, so there's 180 degrees there, and I'll fill that in here after I fill in the other substituents. Okay, and then the 3 R groups, R1, R2, and R3, here they are. They share a plane. Okay, so that plane would be perpendicular to our paper, along the R3 carbon axis. axis. Okay, so let's make a note of some of the things that we saw here. So there's a 180-degree relationship between the incoming nucleophile and the outgoing leaving group. Okay, so the nucleophile attacks 180 degrees from where the leaving group is. Okay, so we call this a backside attack, and I'll write that word out here in just a second. Okay, so something else that's important about the transition state. So in terms of its geometry, it's trigonal bipyramidal. Okay, so that's 5 coordinate at carbon, where then two groups, nucleophile and the X, are 180 degrees apart, and then we have the 3 R groups, R1, R2, R3, that share this trigonal plane. Okay, and that's perpendicular to the axis that's made between the nucleophile, the carbon, and the leaving group. Okay, so we go through this transition state to continue to the products. Okay, so now the nucleophile carbon bond is on the left, and then R1, R2, and R3 have kind of shifted over to the right. So think about, an umbrella. Actually, let me get this written down and then I'll use that analogy. Okay, so think about an umbrella. Like you're holding an umbrella, and the outside of the umbrella is facing, this way, and then the wind is coming, and then you're going to flip everything out to be that way. All right, so we invert the stereochemistry in the SN2 reaction because of this. Okay, so this correlates to an inversion of configuration. And we'll look at some examples later today, to point out, when is it that I have to think about this inversion of configuration. But for now, let's get some the salient points of the mechanism down. Okay, so it's a concerted single-step mechanism. Okay, and then let's make a note about the stereochemistry. So the stereochem, we see what is called inversion of configuration. So in the stereochem is inversion of configuration. Okay, so this is a stereospecific reaction. And we'll see how that plays out a little bit later in class today when we look at some more specific examples. Okay, and then the last thing I wanted to mention was the words that I used, and this is the nucleophile attacks the carbon through something called backside attack. Okay, so this is called backside attack. Okay, and what we mean by that is the nucleophile attacks 180 degrees from the leaving group. Okay, so it's the backside of the carbon leaving group bond, right? And the reason for that is that's where the carbon leaving group anti-bonding orbital is. Okay, so there is a lobe there that we can dump electrons into as we push out the leaving group. Okay, so the last thing that I want to look at here is just, we could draw a reaction coordinate diagram here, and so I'm going to do this just, very quickly here, because there's only a single step, so there's not a whole lot to think about here. So we have the energy on the y-axis, and we have reaction progress on the x-axis. Okay, so as it's a single step mechanism, we'd have something like this, and there's the transition state that we have. Okay, and so depending on, the specific starting materials and products that we have, the energies of the starting material and products might change. Okay, but what I really want to point out is in the reaction coordinate diagram, we have one transition state because it's a single step mechanism. Okay, so one last thing before we look at some of the specifics and look at some examples of this reaction and the specific details, including like what could be a nucleophile in this reaction and what are the properties of the electrophile. I just want to consider then what is happening in the rate determining step of this reaction. Okay, well, what is the rate determining step of this mechanism or this reaction? Well, if there's only one mechanistic step, it has to be that step. Right? So the rate determining step of this reaction is the one mechanism step that we're showing. Okay, so looking at that, what molecules are participating in that mechanistic step? Both the nucleophile and the electrophile. And this is really where we get the rate expression from. Okay, so since both the concentration of the electrophile and the nucleophile are going to govern the rate, this is why it's a bimolecular rate expression. That's where the 2 from SN2 comes from. Okay, so if we were just to, let's make a note here, we're gonna look at the rate expression. Okay, so let's draw out our generic, reaction here. So maybe we had our X plus our nucleophile. We're going to perform this reaction. Okay, so since both the nucleophile and the electrophile participate in the rate determining step, the only step of the reaction, both of their concentrations would be in the rate expression. Okay, so remember the rate is a function of some rate constant K, and then the brackets indicate concentration. So concentration of both the electrophile and the nucleophile are important here. Okay, so brackets are indicating concentration. Okay, so since there's two molecules that dictate the rate, this is bimolecular, okay? So it's a bimolecular rate expression. And so let's just remember that's why it's a 2 in SN2. Okay, so in SN1, well, we're gonna see a different rate determining step, and that's why we're gonna have a different rate expression, and that's why it's gonna be SN1, it's gonna end up being a unimolecular reaction. Okay, so the concentration of both the electrophile and the nucleophile influence the rate. Okay. All right, so let's look at a couple examples, generic examples of SN2 reactions, and then we'll talk about the specifics. Like, as I was mentioning, what are the qualities of a nucleophile that could participate in an SN2 reaction? What are we looking for in the electrophile? Are there any examples of stereochem that we can look at? So those are all things we'll talk about as we go throughout today's class. All right, so our first example, what we're gonna do is we're gonna react this molecule plus this alkyl halide, and we're going to react it in a solvent of THF. THF. Okay, so just a few things about the names of these. Okay, so here we have sodium ethoxide. Okay, so we talked about this back in the acid-base chapter, but remember that oxide ending is telling us we have a conjugate base of an alcohol. So it's the conjugate base of ethanol, so it's sodium ethoxide. And then we're going to react this with ethyl bromide. Okay, and we might just make a note here that this is a primary alkyl halide. We'll learn later on in class today that primary alkyl halides readily undergo these SN2 reactions. Okay, and this specific reaction is called the Williamson ether synthesis because we're going to make ethers. Okay, so this is an SN2 reaction, but more specifically, this process of using alkoxide base / nucleophile and an alkyl halide to make ethers, it's called Williamson ether synthesis, and it's a specific SN2 reaction. Okay, and then I will make one note about THF. We've seen THF before, but something we'll talk about later today is its properties as a solvent. So it's a polar solvent. It's also an aprotic solvent. Okay, and what aprotic means is that all H atoms have a pKa greater than 25. And we'll talk about the consequence of that, or the reason why, we would prefer an aprotic solvent versus a protic solvent a little bit later today. But right now I wanted to look at some general examples so that we can start to think about, what we're going to see in the SN2 reaction. Okay, so the product of this reaction is going to be our ether, and our byproduct would be our sodium bromide, bromide being our leaving group. Okay, so if we wanted to draw the mechanism here, we would have our nucleophilic oxygen attack the carbon that bears the leaving group, and the leaving group would leave. Okay, single step concerted mechanism to make the ether that we have shown there. Okay, so this is called Williamson ether synthesis again because we're making an ether. Okay, so there's one generic example. Let's look at one more and then we'll start talking about some of the important factors of the SN2 reaction. Okay, so let's look at this example. Okay, so here we're going to take alkyl chloride, okay, so chlorocyclopentane, and we're going to react that with sodium cyanide. Okay, so sodium cyanide ends up being a pretty decent nucleophile for reasons we'll talk about, or cyanide specifically ends up being a pretty reasonable nucleophile in this reaction, and we'll talk about, what makes something a good nucleophile a little bit later on. Okay, and then we're again going to use THF here, and we'll talk about other polar aprotic solvents that you could use a little bit later. All right, so in this case, cyanide would be our nucleophile. Okay, so we have cyanide is going to attack the carbon that bears the leaving group, and the leaving group is going to leave. Okay, so our product now is we're going to make a nitrile. Okay, so we now have a nitrile, and that took place of our chloride. Okay, and then our byproduct here would be sodium chloride. Put that in parentheses. I'll make the note there too that this was our byproduct. Okay, so here's two examples. Some things that we could notice about both of these is, we have an anionic nucleophile and an electrophile that is an alkyl halide. So those are pretty good generalizations. But what we're going to do now is we're going to talk about each one of the important SN2 details. So we'll talk about the leaving group, we'll talk about the electrophile, we'll talk about the nucleophile, we'll talk about the solvent. Okay, so let's go ahead and jump into that. Okay, so important SN2 details. And it's these details that are going to help us distinguish between the SN2 and the SN1 reaction once we've learned about the SN1 reaction. Okay, so the first thing is the leaving group. Okay, and we'll abbreviate this as LG. Okay, so basically what's important about the leaving group is that it's a stable anion. Okay, so leaving groups are stable anions. Oh, right, and leaving groups are actually common to all the SN and E reactions. So the SN1, the SN2, the E1, and the E2, they all require a good leaving group. But let's talk about what makes for a good leaving group. Okay, so let's go ahead and draw out a generic SN2 reaction. Okay, so we have our alkyl halide and our nucleophile. Okay, and we're going to think about the rate of this reaction. So we'll just say K rate as a function of the leaving group. Okay, and then the product of this reaction then would be our nucleophilic substitution product and our leaving group. So here is our leaving group. This is the thing we need to be a stable anion. Okay, so what I want you to think about is, as it relates to our class so far this semester, when was the other time that we talked about anion stability? Like, we spent an entire lecture talking about these various factors that control anion stability, right? What were we talking about then? Right, we were talking about acid-base properties, and we were talking about how the stability of the conjugate base dictated the acidity of the corresponding acid. So we're going to think about some of those trends that we considered back then. Okay, so let's look at a series of leaving groups. So we're going to judge or rank the leaving group ability of the following anions. All right, so we're going to look at iodide, we're going to look at bromide, we're going to look at chloride, and we're going to look at fluoride. Okay, so iodide, bromide, chloride, fluoride. If we were to look at the periodic table, they're all in the same group, right, in halogens. And if we think about, as they're related up and down in the same group, what trend or factor, would we compare to get an idea of the stability of these anions? Right, so it was atomic size, right? So as we increase atomic size, we increase the stability of the anion. Okay, so let's make a note about that. So we have increasing stability towards iodide. So increasing anion stability. And we could just make a note there that the trend we were considering is size. Okay, so that means, the more stable an anion, the better the leaving group will be. Okay, so since iodide is the most stable anion because of atomic size, it is going to be the best leaving group. Okay, so as we go from fluoride to iodide, we have increasing leaving group ability. Okay, and if we're just comparing, if the reactions are otherwise the same and all we're doing is varying the leaving group, that means we would have an increasing SN2 rate. So I'll just put that right below. Okay, so a better leaving group gives us a faster SN2. Okay, so the last generalization I want to make then is, good leaving groups are generally weak bases. Okay, so let's write that off to the side and we'll make a note about what some bad leaving groups are. Okay, so good leaving groups are generally weak bases. Okay, and so for now, we could really think about iodide, bromide, and chloride as, three pretty stable anions that would be reasonable leaving groups in our SN and E mechanisms, our substitution and elimination mechanisms. Okay, and we'll introduce a few more when we get to chapter 10. When we talk about alcohols, we'll see there's a few ways to convert alcohols into good leaving groups. Okay, and then the last thing I want to make a note about is, well, if these are good leaving groups, what's example of bad leaving groups? Okay, so strong bases are bad leaving groups, meaning we couldn't do a substitution or elimination reaction when we have a bad leaving group. So some examples of that would be hydroxide or amide, NH2 minus, or hydride, like I can't displace a hydride. Carbon anions would be bad, and even fluoride anions would be bad. Okay, so these are things that you wouldn't do an SN2 reaction on. Like, I couldn't have a nucleophile displace hydroxide and have hydroxide be the leaving group. Okay, so all of our substitution and elimination reactions require a good leaving group. And for now, our good leaving groups are going to be iodide, bromide, or chloride. And again, we'll introduce a few more leaving groups in chapter 10 as they're derived of alcohols. Okay, so now we've seen, what do we require in terms of a leaving group? Okay, so the next thing we're going to do is, well, what is that leaving group attached to? Okay, so, this carbon that bears the leaving group, are there any requirements for that carbon? Okay, so let's go ahead and look at the identity of the electrophile. And this ends up being one of the most important distinguishing factors between the SN1 and the SN2 reaction. Okay, so the electrophile. All right, so we're going to think about the electrophile in terms of their substitution. And this is where we're going to have to revisit the classifications of alkyl halides. Okay, so we could have our halide, our good leaving group, attached to a methyl group, so a methyl halide. Or we could have a primary halide where the carbon that's attached to the halogen is attached to one other carbon. Or we could have a secondary halide. Or lastly, if that carbon that bears the leaving group is attached to 3 other carbons, that would be tertiary. Okay, so there is a rate dependence on the substitution of the carbon that bears the halide. Okay, so it turns out that the rate of SN2, okay, is going to increase with decreasing substitution. Okay, so the rate of SN2 increases as we go from tertiary to secondary to primary to methyl. Okay, so increasing rate of SN2. Okay, and we can be even more specific about that. So methyl and primary alkyl halides readily undergo SN2. Secondary halides have a slow SN2, and we'll see there's lots of competition with other reactions like SN1 and E2. Okay, and then tertiary halides do not undergo SN2. Okay, so they do not undergo SN2. Okay, and we'll see that SN or that tertiary halides are good candidates for SN1. Okay, so if we have a tertiary halide, we can eliminate SN2 as a possible mechanism when we get to the competition between SN1 and SN2. Okay, so let's figure out why this is the trend. Why is it that a methyl halide would be a faster SN2 than a primary? And why is it that tertiary halides can't even undergo SN2? Okay, so it all comes down to sterics. We have to think about the ability of the nucleophile to access the carbon that bears the leaving group. Okay, so let's just consider. So let's take our carbon electrophile, and then let's just think about R generically. Okay, so if R was a hydrogen versus some sort of carbon-based group, and we have to think about the ability of the nucleophile to access that backside of the carbon halogen bond. Okay, so as we increase the steric demand at the carbons, remember sterics is, electron clouds starting to run into each other. So if we have R groups that are carbons, carbon-based substituents, methyl, ethyl, isopropyl, etc., the nucleophile has a harder time accessing that carbon. Okay, so it slows down the SN2. Okay, so we have to think about the steric environment. Okay, so we can make a note over here that, it's harder for the nucleophile to access the electrophile, when the electrophile is more substituted. Okay, so harder for nucleophile to access carbon electrophile when more substituted. And the one word reason for that would be there's a steric problem, right? So the nucleophile starts to run into those various R groups and can't access that carbon. Okay, so if we decrease the substitution of the carbon that bears the leaving group, it's easier for that nucleophile to access that carbon, and we'd have a faster rate of SN2. Okay, and it's that way because we have this concerted single step mechanism. All right, so what is the next trend that we're going to talk about? So we've looked at the leaving group and we've looked at the electrophile. Let's consider what nucleophiles would favor the SN2 reaction. Okay, so third, we'll talk about the nucleophile. Okay, and basically what we're going to see is that the SN2 reaction requires a strong nucleophile. Okay, so now what our goal is to figure out what makes something a strong nucleophile versus a weak nucleophile. Okay, so we're going to make a parallel between nucleophilicity and basicity. And we're going to remember some of the trends that influence basicity. And we'll see that basicity is basically a proxy for nucleophilicity. And let's figure out why that is. Okay, so the first thing I want to say before we actually look at any of the trends is nucleophiles and bases are very similar. You could call them, they're both examples of Lewis bases. They have a pair of electrons to give. Okay, so let's make that analysis. So nucleophiles and bases are similar. They both have either a pi bond or lone pair. And that's the pair of electrons that's going to do the attacking. Okay, so what's different is what they attack. Okay, so what do bases use their pi bond electrons or lone pair electrons to attack? Well, what does a base attack? A base attacks a proton. Okay, so bases attack a proton. And our general mechanism for that could be B, base minus. Let's just use water as a generic acid. So we have our base attack a proton, and then we generate the conjugate base. Okay, so let's consider what a nucleophile is then. Okay, so a nucleophile would attack something else. Okay, so we'll generally say that nucleophiles attack other electron deficient atoms, usually carbon for our purposes. Okay, so for example, if it was an SN2 reaction, note we could use nucleophile now, and let's react that with methyl bromide. Okay, so the carbon of methyl bromide is electron deficient because of the dipole, the electronegativity difference between carbon and bromine. So we have an electron deficient carbon. Okay, so the nucleophile is going to give up its electrons and attack the carbon, and the leaving group's going to leave. Okay, so notice how those two mechanisms are similar. In both cases, the base or the nucleophile uses a pair of electrons to attack something, right? So whether it's attacking a hydrogen or a carbon is really just a semantic argument when we're going to use base versus nucleophile. Okay, so we're really going to think about, how does the structure of that anion influence the basicity and therefore influence the nucleophilicity? So another way to say that is, how available is that pair of electrons to donate to our electrophile, whether it's a hydrogen or a proton, in the case of a base, or a carbon in the case of a nucleophile. Okay, so in general, nucleophilicity parallels basicity. And we'll see there is an exception or two to that, but in general. So generally, nucleophilicity parallels basicity. Okay, so we're going to look at remind ourselves of a few trends. So we'll talk about the importance of charge on nucleophilicity, and we'll talk about electronegativity, and then we'll talk about the steric environment of the anion that's participating as a nucleophile. Okay, so we'll break this up into A, B, and C. So in A, so a negatively charged nucleophile, or let's say a negatively charged species, is more nucleophilic than a neutral species. And here we have to assume the same attacking atom. Okay, so what could we use to compare this? All right, so let's compare our oxygen anion to a neutral oxygen like in an alcohol. Okay, so we have a neutral oxygen versus an oxygen anion. Okay, so the oxygen anion has this excess of charge. And so when it's going to participate in a mechanism, it has a greater, propensity to give away a pair of electrons as a nucleophile because it has an excess of electrons, right? And so since we have a negatively charged oxygen in the alkoxide, that would be a better nucleophile. Okay, so we have a better nucleophile or a stronger nucleophile. So maybe let's change that word to stronger. And then we have a weaker nucleophile. And that trends with basicity too, right? The negatively charged oxygen anion is a stronger base than the neutral alcohol. That's something we talked about, back in chapter 4. Okay, so therefore the alkoxide RO- would have a faster SN2 rate. Okay, so the better the nucleophile, the faster the SN2 rate. Okay, so let's think about one other series of bases that's related to these. So let's compare the alkoxide to acetate to alcohol. Well, we already know that alkoxide's a better nucleophile than the alcohol. We just looked at that. But what about the acetate anion in the middle? how do we know, or the carboxylate anion, how do we know where that falls? Well, remember that that anion is resonance stabilized. So it's not a full negative charge here, right? It's more like negative a half, if you were to consider the resonance structures. Okay, so we're really considering an oxygen with a full -1 charge to an oxygen with a -1/2 charge to a neutral oxygen with no charge. Okay, so we could indicate then we have an increasing rate of SN2. Dang it. Okay, so we have an increasing rate of SN2 as we increase the negative charge from right to left in this case. Okay, and that's because of nucleophilicity. So increasing rate of SN2, the other way we could say that is we have increasing nucleophilicity as we go from right to left in that same series. Okay, so that's one thing we'll look at is charged species. So generally in our SN2 reactions, we're going to see negatively charged nucleophiles. We'll see that in SN1, we can tolerate weaker nucleophiles, and we'll see these neutral species as nucleophiles in SN1. But for SN2, we're typically going to see these anionic nucleophiles, whether it's an oxygen or a nitrogen or a sulfur anion, we will generally see anions. Okay, so the next thing about nucleophilicity we're going to talk about is how nucleophilicity is dependent on electronegativity. Okay, so nucleophilicity decreases with increasing electronegativity. So let's think about that with an example. Okay, so let's compare an amine. So let's look at a neutral amine, so 3 R groups and a nitrogen, and let's compare that to an oxygen that has 2 R groups. Okay, so what is the electronegativity difference between nitrogen and oxygen? Okay, so the electronegativity difference is that nitrogen is less electronegative than oxygen. Okay, so let's think about what it means to be a nucleophile. So to be a nucleophile, we have a pair of electrons and we're going to give them up to our electrophile. So if our atom is less electronegative, it is more willing to give up a pair of electrons and it is therefore a better nucleophile. So in this case, oxygen versus nitrogen. Since oxygen is more electronegative, it does not want to give up its pair of electrons, and so it's a weaker nucleophile. Right? So the trend in nucleophilicity here is that the amine is a stronger nucleophile and the oxygen is a weaker nucleophile. Okay, and so we can actually use electronegativity when we're comparing atoms in the same group as well. So what I want to look at there, whereas we couldn't necessarily do that when we were talking about anion stability and basicity. Okay, so let's look at these two. Okay, so here would be one time that basicity doesn't necessarily track with nucleophilicity. So here we're just going to use the electronegativity. So if you were to look up the electronegativity values for sulfur versus oxygen, sulfur is quite a bit less electronegative than oxygen. So the sulfur anion ends up being a really good nucleophile. Okay, so we have sulfur as it's less electronegative is a stronger nucleophile. And the oxygen anion is a weaker nucleophile. Okay, so notice here, even though we're comparing atoms in the same group, we are using electronegativity. Okay, so electronegativity ends up being more important than polarizability when we're talking about nucleophilicity. Okay, and we're really just going to say, the less electronegative an atom is, the more nucleophilic it is. And you might notice, when I was comparing, the nitrogen to the oxygen, they had the same charge. And when I was comparing the sulfur to the oxygen, they had the same charge. So when you're comparing electronegativity, you need to be comparing species of the same charge. Okay, so the next thing that we're going to consider is the shape of the molecule. And this is another time we're going to see a difference or we're not necessarily going to parallel along with basicity. Okay, so part C is going to be the shape of a molecule. Shape of molecule, and we're really talking about the shape of the nucleophile. Okay, so here we're going to think about how the steric demand at the nucleophilic atom influences its nucleophilicity. Okay, so remember when we were considering the electrophile for SN2, and we said basically the SN2 required an unhindered electrophile. It also requires an unhindered nucleophile. Okay, so let's see how that is going to work out. We're going to compare methoxide to tert butoxide. Okay, so we're going to talk about this through an example. Okay, so we have methoxide, methoxide, and we're going to compare that to this species. Okay, so this is called tert butoxide or T-butoxide. Let's make that more clearly a T-butoxide. Okay, so let's think about the ability of the oxygen anion in methoxide to the oxygen anion in tert butoxide to attack the nucleophile. Okay, well, since tert butoxide's oxygen anion, has this bulky group attached to it, it makes it harder for that oxygen anion of tert butoxide to access the nucleophile. So it ends up being a weaker nucleophile. But if you went and looked up the pKa's, you would see that tert butoxide is actually a stronger base. So here's another time where nucleophilicity and basicity diverge from one another. Okay, so methoxide ends up being the stronger nucleophile because it's less sterically hindered. Okay, so it's less sterically hindered. Okay, whereas tert butoxide is a weaker nucleophile. Okay, and that's because it's sterically hindered. Okay, so let's make some notes about tert butoxide. So it's a weaker nucleophile. Okay, and so why was that? Okay, and that's because it was sterically hindered. So sterically hindered. And that makes accessing the sp3 hybridized carbon electrophile difficult. Okay, so since it's sterically hindered, it cannot access sp3 hybridized carbon electrophile. Okay, so we actually give these bases a name, okay, bases that are not particularly nucleophilic. So tert butoxide is a pretty strong base, but it's a terrible nucleophile. So we call these bases bulky bases, okay? They're also called non-nucleophilic bases. Okay, and they could have a synthetic use, right? Like if I wanted to use a base as a base and I didn't want to worry about it also participating in a reaction as a nucleophile, I would choose one of these. And we'll see just that when we talk about the elimination reactions, the second half of this chapter. So we'll revisit these bulky bases and what their role could be in terms of, eliciting a certain reaction. All right, so these bulky bases are called non-nucleophilic bases, and we have two examples that we're going to consider in this class. So one of them was tert butoxide. Okay, so we already had that structure. I'll draw this in another color though. So another way we could have drawn that is like this. Inline angle formula. So this could be potassium, lithium, sodium, tert butoxide. And we would abbreviate this as T-Bu-O minus. Okay, so that's the abbreviation you could see, and it could have a counter ion there, sodium, lithium, potassium, +1 cation, so tert butoxide. The other one we have is something called LDA, and here's its structure. Okay, so LDA is the nitrogen anion. It always has lithium as a counter ion. This is called LDA, and that stands for lithium diisopropyl amide. Okay, so that nitrogen anion gives it that amide ending. Okay, so LDA and tert butoxide have in common that they are strong bases, but they are not nucleophilic. And again, that's because they're sterically hindered and cannot access the sp3 hybridized carbon electrophile. Okay, and we'll see that we can use them for very specific reasons a little bit later in this chapter when we talk about the eliminations. Okay, so now we've talked about nucleophilicity, and in general, just as a recap, we are going to think about, anions as our strong nucleophiles, and we'll consider things like electronegativity and the steric environment of our nucleophile to access or assess whether or not a nucleophile would be strong or weak. Okay, and I'm actually going to pull your attention to this chart that's in our book. I'll go ahead and post it into our notes at this point. But we have a table in our book, which is basically shows us the trend in nucleophilicity. Okay, so you can go ahead and look at that and get a feeling for the wide variety of nucleophiles you could use. So here we see acetylide that we used, in our first SN2 reaction we considered. Here we have the alkoxide anions we've been talking about today. We can see those sulfur anions that we talked about earlier today. And so this is a good reference table just to get an idea of what different kinds of nucleophiles you could anticipate within a reaction. Okay, so one of the next things that we need to talk about, so we have two more things to talk about for the SN2 reaction. So the next thing we're going to talk about is the solvent. Okay, so the solvent for SN2. Okay, so the SN2 reaction is best in polar aprotic solvents. Okay, and so we saw that with THF, but what are some other examples of polar aprotic solvents? And why do we want a polar aprotic solvent? Okay, so what does polar mean? Well, we know what polar means. We have a polar molecule with polar covalent bonds. Okay, and so why we'd want a polar solvent is because it stabilizes the polar species, like the nucleophile in the transition state. Polar species. Okay, and we're really thinking about the transition state. So if it stabilizes the transition state, it'll bring the energy of the transition state down. That will speed up the reaction and facilitate the SN2. And why do we want it to be an aprotic? Okay, so again, aprotic means that all hydrogens in the molecule have pKa greater than 25. Okay, so the reason why we want aprotic solvents is because then the solvent does not interact with our nucleophile. So the way we say that is it does not solvate. So solvate means, a solvent molecule interacting with our whatever it is. Okay, so we do not want our solvent to solvate our nucleophile because that would make it less nucleophilic. Okay, so does not solvate anions well. Okay, and that would be our nucleophiles. We want our nucleophilicity to be high for reasons that we've talked about already. SN2 favors strong nucleophiles. Anything we do that influences the nucleophilicity and makes it a weaker nucleophile slows down or hinders our SN2 reaction. Okay, and the way that these, protic solvents, so if I did have these polar, if I had these protons that had pKa's less than 25, they would interact with our anion nucleophile through hydrogen bonding. Okay, so the way that they would solvate is through hydrogen bonding, through H bonding. So that doesn't occur when I don't have these hydrogens. And we'll look at an example to elicit that here in just a second. Okay, so since we don't, hold on one second, I need to pause for just a second. Okay, sorry about that. So what I was saying was the aprotic solvents, they do not solvate the anions well, okay? And the anions are nucleophilic, are nucleophiles, okay? And the way that the solvents could potentially solvate our anions would be through hydrogen bonding, okay? And so we don't see these hydrogen bonding interactions with aprotic solvents, okay? And that keeps the nucleophilicity high, okay? So let's just make a note with that. Keeps nucleophilicity high. Okay, so let me show you examples of polar aprotic solvents, and then we'll look at a comparison between a nucleophile in a aprotic and a nucleophile in a protic solvent. Okay, so what are our other polar aprotic solvents? Okay, so we're looking things that have polar covalent bonds and don't have any acidic protons. Okay, so one we already saw was THF. Another one is this molecule, dimethyl sulfoxide, DMSO. Dimethyl sulfoxide. This solvent is also important because it is a common solvent for dissolving chemotherapies when they're given to cancer patients. So you might hear of that molecule again at some point. It has a very distinct smell. Another one is acetone, like nail polish remover, acetone. Another one is acetonitrile, so a methyl group attached to a nitrile. This is acetonitrile. And then our last one is something called DMF or dimethylformamide. So it's an amide with two methyl groups. So this is DMF, which stands for dimethylformamide. Okay, so notice that all of these molecules only have hydrogens attached to carbons. There's no hydrogens on oxygen, there's no hydrogens on nitrogen. Therefore, there are no acidic protons. And so since there's no acidic protons, those protons that don't exist, aren't going to interact with our solvent. Okay, so let's consider, let's compare methoxide in a polar protic versus a polar aprotic solvent. Okay, so we're going to look at methoxide as our nucleophile in THF versus, well, what's an example of a polar protic solvent? Something like methanol, something that has an OH, an NH, an SH bond, some acidic proton. Okay, so we have the structure of THF over here. Okay, and then let's think about how might that molecule interact with methoxide. Well, there's not a whole lot going on there. There are some, the polar bonds within our THF, like the carbon-oxygen polar bond, those, partial charges might interact with our oxygen anions. Okay, so now let's compare that to methanol. Okay, so here, if I were to consider the structure of our alkoxide, okay, and then let's draw in some of our solvent molecules. So remember that that OH bond is quite polar. And when we have that polar OH bond, that hydrogen then can participate in H bonding. Okay, so we have the potential for 3 different hydrogen bonds between that oxygen anion of our nucleophile and the solvent molecule. So that's an example of solvation. Okay, and so if you think about that oxygen anion's ability to be a nucleophile in this case, what would have to happen first is we would have to, break all these these hydrogen bonds between oxygen and the protons. We'd have to break all those hydrogen bonds before that oxygen anion could act as a nucleophile. Okay, so let's just make a note of that. Okay, so solvation would need to be broken. So solvation needs to be broken for SN2 to proceed. Okay, whereas with THF, there was really minimal interaction between our solvent molecule and our nucleophile. Okay, so for those reasons, SN2 is going to favor strong nucleophiles. Nucleophiles are stronger in polar aprotic solvents, and that's why we see aprotic solvents as the main solvents in these SN2 reactions. Okay, so the last thing that I want to talk about today is going to be the stereochemistry. And we also actually already looked at this when we were looking at the mechanism, but I want to look at some examples. Okay, so the stereochemistry. So the stereochemistry of SN2 is we are going to have inversion of configuration. Okay, and this is due to that backside attack. Okay, so let's look at an example. Let's take cyanide as our nucleophile and let's react it with this secondary alkyl halide. Okay, so our mechanism is our nucleophile attacks the backside of our leaving group. Okay, so remember that umbrella analogy where we have the umbrella, flipping out in the wind going the other direction. So the new bond between the nucleophilic carbon and the carbon of our electrophile are on the left-hand side of the molecule, but all the other substituents, the ethyl group, the methyl group, and the hydrogen, they flip from left to right. Okay, so that is inversion of configuration. If you assigned the R and S, you would see that you went from R to S, right? We inverted the stereochem. And again, that's because of the backside attack. Okay, so I want to just look at 2 quick examples of this to see what it might look like in line angle formula with some actual molecules, and then we'll be done for today. Okay, so let's take this secondary halide, and we're going to react it with potassium cyanide, and we'll use acetone as our polar aprotic solvent. Okay, so mechanistically, we would have our cyanide nucleophile attack our carbon and the leaving group leaves, and this is going to happen through inversion of configuration. So if the leaving group was on a wedge, the incoming nucleophile would be on a dash. So inversion, this is stereospecific. The absolute configuration of the electrophile, the carbon leaving group bond, that configuration influences the stereochem of the product. Okay, and one last example, let's look at an example of something in line angle formula, or a non-cyclic molecule rather, and let's use this sulfur anion in DMSO. Okay, so our mechanism would be our sulfur nucleophile attacks the carbon that bears the leaving group. If we go by inversion of configuration, since the leaving group is on a dash, the incoming nucleophile would be on a wedge. Okay, so we can see how both of these correlate to inversion of configuration. If the leaving group is on a wedge, the incoming nucleophile comes in on a dash. If the leaving group was on a dash, the incoming nucleophile comes on a wedge. And we don't see a racemic mixture here. We get inversion of configuration only. Okay, so if we have an optically pure starting material, we'll get a single optically pure product, okay, through inversion of configuration. And we'll see that that is one of the distinct differences between the SN1 and the SN2 reaction. Okay, so we've talked about most of the important features of the SN2 reaction, and what's left to talk about it is really, given that SN1 and SN2 are similar, when is it that SN2 is going to dominate and when is it that SN1 is going to dominate. So what we'll do on Friday is we'll talk about the SN1 reaction, and then we will go ahead and say, well, under these conditions, SN1 would occur, and then in these other conditions, SN2 would occur. And we'll play this really fun game called SN1 versus SN2. And then we'll be ready to incorporate the elimination reactions just to make that game even more fun, because then it becomes SN1 versus SN2 versus E1 versus E2. All right, well, I'll be back on Friday to tell you more about the SN1 reaction.